So, let us revise what we did in the previous lecture. We talked about vector potentials, magnetic vector potential. In magnetostatics, we use this. Later on in the waves and time varying magnetic fields, this vector potential has also different meanings and applications, but nevertheless the vector potential is the defining equation that B should be equal to curl of A. The magnetic field is curl of this vector, and this is known as vector potential, and we did lot of algebra and lot of things, and we found that there is a mathematical similarity between the charge distribution and its electric potential, and on the other hand current distribution and its magnetic vector potential. And for that we showed that this del square operator, which we call Laplacian, and this Ax, Ay, Az, they follow this Laplacian equation, that is del square of Ax will be minus mu naught Jx, and similarly for y component and z component. And this same del square of a scalar field is equal to some distribution here that also comes in electrostatics, and that we saw that del square of electric potential is charge density by epsilon naught with a negative sign, and here it is del square of this component of vector potential x component is again minus mu naught times this x component of the current density. So, this similarity in the mathematical structure gives us an easy way to find the vector potential if the current distribution is given. And what is that? What is that? You look at these equations in electrostatics. If we have a charge density, and then in a small volume we have this charge. So, that charge divided by the distance and 1 by 4 pi epsilon naught, that is the potential, electric potential due to that charge distribution. Exactly the same thing here, here it is, this is charge, small charge here, and then 1 by 4 pi epsilon naught and the distance, and the similar structure is here. Current density is given to you, x component of current density. We will have separate calculations for Ax, Ay and Az. For each of the component Ax, Ay, Az, this recipe is to be used. I am looking for Ax, x component of vector potential, then the current density is given to me everywhere, wherever there is a current, and we will assume that x component of that current density is actually a charge density. That same function we will assume that it represents a charge distribution, and for that charge distribution we will write what is the electric potential, and we will get some expression, and then epsilon naught will be replaced by 1 by mu naught, or 1 by epsilon naught will be replaced by mu naught, and that is it, we will get the component. So, that is the meaning of these equations, and this thing is in terms of the volume current density, volume current, but if you have surface current or linear current, then you use correspondingly J d tau is replaced by K dA or I dl. So, that is the way we will be calculating. So, we will start with an example, and then this whole procedure will be better understood. So, our example will be surface current on xy plane. We had done it earlier using the standard method of calculating magnetic fields, Bat-Savart law, and also this Ampere's law, we had done that. So, let us take that same example. We have a large plane here, xy plane, this is x axis, this is y axis and this is z axis. And on this large plane we have current, surface current, and the surface current density is K. Surface current density is K I cap. And we want to know the vector potential because of this current which is flowing on the surface of this xy plane here as well as here in the entire space. So, what we will do, let us first see that this current density has only the I component. It does not have j component, it does not have k component, no component in y direction and no component in z direction. Therefore, A y will be 0 and A z will be 0, first thing. Because for getting A y, we will take the y component of the current density which is 0, and then if you assume that that is the charge density, there is no charge density, it is 0. So, no potential, 0 potential everywhere. So, A y and A z are 0. To get that A x, what we will do? We will see the x component of the current density. Those steps just keep in mind. First thing is, what is the x component of the current density, and remember this is our surface current. So, our equation is in terms of surface current. So, it will be mu naught by 4 pi here and then integration k dA and then divided by r minus r prime. Alright. So, for A x we will only take that x component and treat this this k x component of k is just this k, this k, the whole k here, that is the x component. So, we will assume that this is representing a charge density, a surface charge density. Where is this current? This current is only on the surface. So, this k represents, mentally we are assuming it is representing current density, surface current density, but we are, for our mathematics purpose, we are assuming that this represents a surface charge density, wherever that current was. So, now I have xy plane, and then everywhere we have charge, and the surface charge density is k. So, we have done all this. If you have a large surface charge, plane surface charge, uniform surface charge density sigma, then we know the electric field on this side will be sigma over 2 epsilon naught this direction, and below the surface it will be E equal to sigma by 2 epsilon naught in the downward direction. So, that is the electric field due to a large surface charge density on a plane. Because of this charge distribution, what is the electric potential? So, let us write, if this is the charge distribution, which is k, in fact this k is taken as the surface charge density, but let me first do it in terms of sigma, because this sigma by 2 epsilon naught is our very familiar expression. So, what is the potential? How do I write the potential? So, normally we take potential at infinity to be 0, but since this is itself is extending to infinity, we take potential 0 on this surface. And then as you go up, the electric field is in upward direction. So, the potential will decrease. Here it is 0, here it will be negative. And how will it go? Our expression should be, if this is z direction, then your Ez should be minus del V del z. And since this Ez is constant, it is sigma by 2 epsilon naught. So, you can immediately do this algebra and write this V as minus sigma by 2 epsilon naught times z, right. So, that when you do this minus dV by dz or minus dV dz, you will get sigma by 2 epsilon naught, which is the z component of the electric field. So, this is the potential here. If you take this k as the surface charge density, then this expression is minus k by 2 epsilon naught and then z. You only have to replace this 1 by epsilon naught by mu naught, and you write now it is minus here and then 1 by 2 here and mu naught here and then k here and z here. What I have done? First I have calculated the potential, electric potential, assuming that you have a surface charge density on this, and that surface charge density is k. So, from there we wrote the potential, electric potential, surface charge density sigma k 2 epsilon naught z, and then we replaced 1 by epsilon naught by mu naught, and I have gotten our Ax, and Ay and Az are anyway 0. So, for z greater than 0, we have the expression A is equal to minus mu naught by 2 and then k z and then x. So, this is I cap, this is I cap. Yes, come down here. The electric field here is sigma over 2 epsilon naught in minus k cap direction, So, if I take Ez, that Ez should be sigma by 2 epsilon naught with a negative sign. The electric field is downward, here the electric field was upward. So, what is V then? The potential is sigma over 2 epsilon naught and then z. Since it is 0 here, if you are going down, you are going in the direction of the electric field. If you go in the direction of electric field, the potential decreases, therefore, it should decrease. Z itself is negative here, and therefore, it will be negative, and this is the right expression. And from here, if you write this A for z greater than 0, if you write this A, then this A will be mu naught over 2, and then this sigma is actually k. So, k here, and 2 epsilon naught, 1 by epsilon naught has become this, and therefore, this z here, and this is capital K and I cap. So, this is for z less than 0. This is for z greater than 0, this is for z less than 0. Simple? Simple, at least this example is quite simple. We have just taken a current density on xy plane and uniform current density k in I cap direction. That k, I mentally assume that it is not the current distribution, it is the charge distribution, it is the surface charge density. And then we write the potential, electric potential, and the expression we get in that we replace 1 by epsilon naught by mu naught, and we get the vector potential. Now, let us get the magnetic field due to this surface current using this vector potential. All right. So, let us take that expression for z greater than 0. A is for z greater than 0, A is minus mu naught by 2 minus mu naught by 2 and then k, z and I cap. B will be curl of A. This is all in Cartesian coordinates, so our expression is simple. For getting this curl, you can write the determinant I cap here, j cap here, k cap here, del x here, then del y here and del z here, and then the components x component, y component and z component. And in our case, this is I cap, j cap, k cap, del x, del y and del z, and then x component of A is here minus mu naught k z by 2 and then y component and then z component. Then expand. First is take this I cap here and then omit the row and the column containing that I cap. You are left with these 4, then del y of this quantity minus del z of this quantity is 0, because it is 0 here, it is 0 here. Del y of this minus del z of this, so 0. So, this part is 0. Then you have minus j cap. I hope you remember how to open up determinant in algebra. So, either you can write plus j cap and then del z of this quantity and minus del x of this quantity, this is possible, or you write minus j cap, omit the rows and columns and then you have del x of this and minus del z of this. So, 1, 2, 3, 4, same story, del x of this and del z of this, but then you put minus here. So, del x of 0 is 0 and then minus what? Del z of this. So, del z of minus mu naught k z by 2, and that is minus j cap here, this minus and this minus becomes plus, and del z. So, here z in the first power. So, the differentiation will be just mu naught k by 2. This minus I am writing here, this minus and this minus I am making it plus, then del z of z is 1. So, it remains this. So, that is it, you have gotten your magnetic field. So, magnetic field is mu naught k by 2 in minus j cap direction. That is what we had derived earlier using Ampere's law or Biot-Savart's law. And similarly, if you are for z less than 0, you use that expression and your B is minus was here. So, this will be without minus mu naught k by 2 j cap. Take one more example, and this example will be a rectangular or a square loop, current loop. So, suppose we have a square loop, this is a square loop and we have current I here, A, B, C, D, and can take origin here, x axis this way, y axis this way and z axis coming out of the board. This will be z axis and then we need vector potential at a general point, say x, y, z. And this is now linear current. In the previous example, we had taken surface current. This time it will be linear current, and correspondingly we will assume that whatever is the linear current given, that will be I, in fact linear current I, right, this J d tau replaced by K dA replaced by I dL. If it is linear current, then this J d tau becomes I dL. So, that is it. So, this I current here, 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 here in the 4 arms, we will take it separately. So, to get this vector potential at this point here, what we will do? We will mentally assume that its current, this I represents a linear charge density. This I represents a linear charge density, and then if I look at this AB, let us draw the diagram again. This is AB. So, on this AB I have charges, positive charge, x component, remember x component, this is in x direction, current is in x direction. So, we will take x component of whatever, this or this or this. So, here the x component is in positive direction. So, we are taking it positive charge I, and then you have BC, current is in y direction. So, we will first look at this. This current is also in x direction. This current in CD, this I goes here and goes here. So, that also let us draw. So, that current in x direction will be taken first. So, this is CD, and then since we have to take the x component, and dl this time is towards left because of this arrow. So, we will say that it has a negative minus I charge density. I repeat, this is not charge density, it is current here, linear current here. Only for calculating vector potential we are doing this trick, that we are drawing a diagram showing positive charges sitting here with a linear charge density I, and negative charges sitting here with a linear charge density I. Now, because of this we want magnetic potential, vector potential at x, y, z. Assume it is far away, from the current loop. This length, let us say, is A. This length is A, and this distance OP is very large as compared to this A. Far away means you have to tell what this far away means. So, there has to be some length with respect to which you say that the distance is very large. So, here the length of this edge of this square, this length, that gives me the scale. With respect to this A, this distance is very large, then we will say that it is a far away point. Now, for that, you can treat this as an electric dipole, right? And for electric dipole, let me revise equations. First is the dipole moment is defined as integration of r vector dq. What is this? In high schools, we normally define electric dipole as a combination of two charges, nothing wrong in that. But then you may have a bigger charge distribution. At some places the charges are negative, at some other places charges are positive, total charge 0. Then also we can define a dipole moment, and for that we do this. If charges are distributed in this volume, at some places it is negative charges, at some places it is positive charges, variable, at different points you have different magnitudes of charge densities, etc., etc. So, you take a small dq, take some axis, and then this is r vector and this is d tau. Whatever charge is here, that charge you write here, and then multiply by this r vector and then integrate, that gives the dipole moment. Minus q plus q is also all right. This is minus q, this is plus q. Since it is discrete, it will be summation I q I r I. And if you do for this, you get your familiar q d. P is q d from negative charge to positive charge, minus q to plus q. And if you have an electric dipole, this kind, if you have an electric dipole with dipole moment P, if you know that dipole moment, then the potential due to this, suppose this is the direction of dipole moment, it is in this z direction, this P is a vector, and you need electric potential at a far away point at a distance r, and if this angle is theta, which angle is theta? The dipole is here, and then the field point where the potential is needed is here, and then this is vector r, and this is the direction of dipole moment. So, the angle between this position vector r of the point where the field is needed and the direction of dipole moment, that angle is theta, and then V is given by 1 by 4 pi epsilon naught and P, magnitude P, and then cos theta and divided by r square. Okay. So, these things are from electrostatics. The potential due to an electric dipole at a point, far away point, is given by this expression, and these are the meanings of these symbols. So, our task will be, this is a dipole, get the dipole moment, magnitude and direction, and using this equation write the expression for electric potential due to this electric dipole at a faraway point x, y, z. And once that expression is obtained, the only task left will be replace 1 by epsilon naught by mu naught, and that particular component of this vector potential will be ready. So, we will complete this task in the next lecture. We also have to consider these two arms and similar kind of analysis, and we will get our vector potential.